I will begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for the students. Just ask you to bless this class today, Lord. In your name I pray. Amen. Okay, so before I forget, let me just say a word about isometries. What's an isometry? No clue? Yeah. So I'll focus. Yeah, isometric. Yeah, that's true. Which means the same measure. Iso means same. Yeah. So I'll focus on a particular case of this idea, Rn, with the Euclidean distance function. How do you define the Euclidean distance between 2 points? So let's use d for distance. So d, if I take a point P, if I take another point Q, what's the distance between P and Q? How do you calculate the distance between P and Q? In terms of norm. If this is P, this is Q, what do? You look at the vector that goes from here to here, right? And whatever that vector is, I mean specifically it's Q minus P, right? So you just take Q, the length of Q minus P, that's the distance between points P and Q. You know, if we look at 2 dimensions, this gives you the 2-point, the distance formula between 2 points that maybe you learned in middle school or something, right? In 3 dimension, it gives you the square root of the sums of the squares. You know, I can be less vague. This is just Q1 minus P1 squared plus Q2 minus P2 squared plus dot 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 plus Qn minus Pn squared, like that. So an isometry of Euclidean space, and Euclidean space is Rn paired with this distance function, all right? Rn paired with this notion of distance is called Euclidean space. An isometry of Euclidean space is a function f which goes from Rn to Rn and preserves distance between points in the sense. So the distance between f of P and f of Q is equal to the distance from P to Q. This is what's called an isometry. All right? Now, if the students haven't worn me down too much, if I'm not too tired in a given semester, I will ask them to prove certain things about isometries in abstract algebra. You can prove the following. Any isometry is the composition of an orthogonal transformation and a translation. Now, goodness gracious, a translation. So this, by definition, if you look at a composition of a translation and an orthogonal transformation, is what's known as a rigid motion. So, a rigid motion. Let me just take a second to show you an example. If we let t of x equal to x, let's say x plus a for fixed a in Rn, then this is what's called this is a translation by a. What's that? I want to explain to you why this is an isometry. Why is this an isometry? Why is translation First of all, is it a linear transformation? Well, if a is not equal to 0, we're in big trouble, right? Because what's t of 0?
0.
No. T of 0 is a. So did I say a was 0?
Oh, that makes sense.
Oh, no. I mean, if a is equal to 0, we're okay, right? But a linear transformation has to map 0 to 0. So unless a is 0, translation is not linear, right? So translation it's an interesting function, but it's not a linear function. What's the inverse? How do you undo adding a? You subtract a. There you go. So apparently this is a bijection, right? But it's not a linear bijection. It's something else. Is this an isometry? Well, it's pretty easy to check. D of t of p, t of q is the length of p plus a, t of q minus t of p, right? Which is what? Q plus a minus p plus a. So the a's cancel, and you've just got the q minus p, right? So that's the distance from p to q. So certainly a translation preserves the distance between points, right? And last time, I mean, if you have, t orthogonal, what did that mean for us? What did we say that by definition meant what? In this context, t of x dot t of y equals to x dot y, right? So, of course, if you look at the distance, I mean, that implied, among other things, that the length of t of x was equal to the length of x, right? I mentioned that last time. So if we look at the distance from t of p to t of q, what do you got? For an orthogonal transformation. But an orthogonal transformation is what? It is linear, right? So a linear transformation allows me to rewrite that as q minus t of q minus p, right? But that's by definition, I mean, by this putting x equal to q minus p, what we did last time, right? That's the length of q minus p, which of course is the distance from p to q. So as you can see, if we have an orthogonal transformation, it's also an isometry. And it's a simple exercise to show if you compose isometries, you get an isometry. So the composition of isometries is once more an isometry. In fact, the set of isometries with respect to a particular geometry, it forms a group called the isometry group. The isometry group for Euclidean space is just the group of rigid motions, which again are like translations and rotations or reflections, because an orthogonal transformation has both rotations and reflections. These are the allowed motions in physical space which, maintain the shape of objects, essentially. Actually, to be fair, I can't have determinant negative for a physical motion. Like if you think about determinant being negative, that corresponds to like ripping things inside out. If you study it more carefully. So we actually should insist on, we should be careful. Some of the orthogonal transformations might not be quote unquote physical motions. They might be motions that preserve distance, but they don't preserve orientation in a way which is reasonable for motions of physical objects. If you can't go from a cube being left-handed to a cube being right-handed without tearing it inside out, so to speak. Right-handed meaning that you go length, width, and height, and like the length direction cross the width direction is the height direction. If it was left-handed, the length direction cross the width direction would be the height direction. So it's the handedness of the cube gets spoiled by determinant -1 things. Now, great. It's not at all, do you see anything? What's missing here? Did I say a linear function? No. So this is actually a pretty hard thing to prove, that those two things composed is it. There are like no nonlinear isometries of Euclidean space. You can prove that preservation of distance forces linearity for the isometries which fix the origin. So if your isometry fixes the origin, it has to be an orthogonal transformation, right? And if it doesn't, it can be written as the composition of a translation in an orthogonal transformation. I won't prove that in here. I sometimes assign it as an abstract algebra homework. It's actually pretty difficult to prove. If you're interested, ask me. I can send you a link. I do it in a video somewhere in a course I shot for a student a few years ago. Anyway, that's that. So that's what an isometry is. Some of you were wondering what isometry was. This is what an isometry is. For the most part, we're interested in orthogonal transformations because those are isometries of Euclidean space. In the same sense, you could look at Cn paired with the distance between points in the complex sense. All right? And for those, the unitary transformations are example of isometries with respect to the complex notion of distance. You could look at other spaces paired with some notion of distance and look at the set of transformations which preserves that notion of distance. Those would give you yet other kinds of quote-unquote isometry groups. But that's more of a story for group theory, so I'll leave it for there. Yeah? Now, so I almost got to the punchline last time. Let me get to it this time. So here's the punchline. So we defined the adjoint, all right? Remember last time we talked about T from V to V, linear transformation. If beta, V1, V2, Vn, orthonormal basis, then the adjoint, how do we define it? What was it? It was the sum I equals 1 to n of, I want to say it was the inner product of T of x with Vi, Vi. But I could be wrong about that. Am I wrong? Oh, man. Okay, so it was supposed to be, and is that T of Vi or is that T of x? T of Vi in the first slot and x in the second spot?
Actually, x is in the first slot. What do you have written down?
Oh, I got you. So I've picked one of the wrong flavor. So x like that and T of Vi over here?
Yeah.
Thank you. All right. So that was the definition of adjoint. So that gave us a new transformation. All right. This is called the adjoint of T. Right. And then we had an additional definition, which was that T is normal if it commutes with its adjoint. If T star is equal to T star T, right? T is self-adjoint if T is equal to T star. All right. So I wanted to run back through all that terminology to make sure that when I write the theorem I'm about to write, it's at least a little bit more familiar. I know you haven't done the homework on this yet, but okay. So here's the theorem. If T, well, no, let me state it more. Let me state it as I ought to, which is This is theorem 9.6.16 on page 295 of my notes. So, yeah, I will. I'll write it down here. 9.6.16. That's on page 295. And so with t as above, for t going from v to v, linear on real inner product space, then t is self-adjoint if and only if there exists an orthonormal eigenbasis for t. So t is self-adjoint if and only if you can not only diagonalize t, but you can do it in an orthogonal manner. You can do it with an orthonormal basis, in fact. So this is the celebrated real spectral theorem. Now, the next thing I'll write, it's not even proved in my notes, but I'm mentioning it for the sake of your edification here. I'm going to show us examples of this real spectral theorem here shortly, all right? But in the complex case, all right, well, okay, fine, I'm getting out of order here. I'm sorry, I'm jumping the gun. Theorem 9.6.17, I should say first. So 9.6.17 says that there exists P, an orthogonal matrix. All right. So here I'm given A in Rn by n. Okay. I'm stating the corresponding theorem for real n by n matrices. All right. There's obviously, there's a correspondence between linear transformations on real vector spaces and real n by n vectors, real n by n matrices, right? So there exists P, orthogonal matrix, for which P transpose AP is diagonal if and only if, and this is really, really complicated, so, pay close attention. I'm joking. Look at that. So a matrix is diagonalizable by an orthogonal matrix if and only if it's a symmetric matrix. This is very nice because orthogonal matrices are the easiest kind to invert, right? Like when we think about a similarity transformation, compare this to P inverse AP equals 2 diagonal, sort of in the wild, right? Usually the inverse matrix you can't just form by transposing the matrix P. If the inverse of the matrix is the transpose of the matrix, that means that the matrix satisfies P transpose P equal to the identity. That means that the columns of the matrix are an orthonormal basis for the space. That's very, very special. So this is, outside of very nice P inverse equals to P transpose case. And this is to say that P inverse equals to P transpose. So I is equal to P transpose. Or you could multiply on the other side and get P inverse P equals to P transpose P, which gives you I is equal to P transpose P, right? So if your matrix satisfies P transpose P equals the identity, it also satisfies P times P transpose equal to the identity. Because, of course, you could take the transpose of the equation and get from one to the other by sock shoes for what it's worth. But anyway, so that's theorem 9.6.17. What I was jumping ahead to a minute ago is that there's a corresponding theorem for complex matrices, all right? And the corresponding matrix for the corresponding theorem for complex matrices, which I'll find the right color eventually here, theorem 9.6.18. It says that given, you know, is it A or did I do U? I can't remember what my notation is. U. Given U in Cn by n, there exists, do I use P or do I use Q? P. There words. Exists P in Un, I think was my notation, for which, oh, goodness. Now I forget. Oh, P star, yeah. P star A. Oh, I did not use U there. I see what you're saying, Nathaniel, but that's an A. So sorry.
Are you talking about that?
Yeah.
Okay.
P star AP is equal to, is diagonal.
I thought that's what you were
Yeah, I got you. So what does the P star here mean? Do you guys remember? We defined that last time. Yeah, conjugate transpose in this context. So what's the condition that a complex matrix is, you know, orthogonally? Well, this is the complex analog of orthogonally. It's unitarily diagonalizable. Some books would also just call this orthogonal, just it's complex orthogonal. So it's actually the normal condition is what you need here. So A commutes with its adjoint. So, I mean, theorem 9 point, well, I'll shut up. But, I mean, I think you can see 9.6.17 as a special case of 9.6.18 if you think about it, at least in part. So, all right. So most of my focus going forward is on the real case, all right? So the real spectral theorem, it's quite beautiful because all we have to do is check, is the linear transformation or is the matrix we're looking at symmetric? If it is, that means we can find an orthonormal eigenbasis. And you're like, well, that's great, but I don't care about either of those concepts. No, that's not what you're saying. Not that you don't care, but both of those concepts at this point in my life, in the midst of all the other things going on this semester, are not especially like you're taking two things I partially understand and putting them together to make something I even less partially understand, right? I mean, so it's like, it's not nice, right? Let me try to convince you that it's nice. I can try. I'm going to try. So, yeah, one more definition, then we'll be done with definitions. But the one, we've talked about projections before, but now I need to refine that notion a little bit more. I'll talk about orthogonal projections. So V an inner product space, and S a linear transformation from V to V, for which, here we go, the range of S, the perp of that is the kernel of S, and the perp of the kernel of S is the range of S. If you got those, if you got these, all right, is called an orthogonal projection. If we can find a linear transformation like that, it's called an orthogonal transformation, orthogonal projection. All right. Excuse me. So let's look at an example. I'm going to try to build some of these orthogonal projections with a specific example, okay? Let's keep it relatively simple. Let's look at like a 2x2 case. So you guys, you pick your favorite 2x2 symmetric matrix, whatever you guys want. No, I need numbers. 1, 2, 3, 4. I'll take your 1, 2, 2, 3. There you go. Now it's symmetric. So I trade your 1, 2, 3, 4, 4. I mean, I don't disapprove, but anyway, there you go. And I'm going to change that 3 to a 1.
That's not my favorite matrix.
Oh. But
It's okay.
well, I mean, I will consider putting it.
We're gonna erase this number like 4 times. The easiest.
So what's the determinant? Well, here, I'll tell you what, I'll put a C there for now, pending our choice. Well, let's choose a value for C which makes this example like not horrible, right? So, yeah, see, if we put C equals to 1 there, then we get the difference of squares, so the algebra works out pretty nice. If we put 3, it might still work out nice. I don't know. I mean, I'm trying to. I'll stick with 1 just because we got other fish to fry here today. So here, -4. So that's lambda -1 -2, lambda -1 plus 2, right? Also known as lambda -3 times lambda plus 1. All right. So my point is the eigenvalues are lambda 1, which is, let's say, 3, and lambda 2, which is -1, right? Now, if you believe this real spectral theorem, I'll fix it. I know it's bothering some of you. Oops. All right, anyway, let me stop. If you believe the real spectral theorem, we better be able to find eigenvectors, and not just that, we better be able to orthonormalize them, right? Can we do that? What's for lambda 1 equals to 3? We're looking at what? A minus 3i, which is equal to what? Looks like -2, 2, 2 minus 2, right? So that says to me that the eigenspace with eigenvalue 3, right? Or let's say call that E1, should be the span of, well, 1 over the square root of 2, 1, 1. Do you see why I did that? Because 1, 1, when I multiply 1, 1 by the matrix, I get 0, right? Which means that it's in the eigenspace with eigenvalue 3. That's a basis for the null space of A minus 3i, right? Now, for a more complicated problem, maybe I need to write out some calculations. But I personally think it's very reasonable to write down answers in this particular 2 by 2 case, right? You guys help me out. What about the next one? Lambda 2 equals minus 1. We've got a plus I, which is what? It isn't. Yes, nothing to sneeze at. Just 2, 2, 2, 2. Let's see here. So E2 is the span of what? I want to put the basis for the null space of A plus I, right? Because that's the eigenspace with eigenvalue minus 1. And I'm normalizing it as I go, just to, get it over with. How about 1 over root 2 times what? I want to make it a unit vector, because I'm trying to illustrate the real spectral theorem by finding an orthonormal basis of eigenvectors. You got 2 choices, right? Geometrically, what's going on here, we can picture, it's the plane. So here's your V1, right? So for V2, you can either put it over here, or you can put it over there. Either one of those will give you a legit orthonormal eigenbasis here. Personally, I like 1 minus 1. So I guess I choose that one. I don't know. Maybe the other one's a better choice. Yeah. Whatever. Anyway, there it is. So what am I going to do with these? So beta, 1 over the square root of 2, 1, 1. 1 over the square root of 2, 1 minus 1, is orthonormal eigenbasis for A, right? In fact, if we let P equal to 1 over the square root of 2, 1, 1, 1 minus 1, then P transpose is equal to P in this case. This matrix is its own inverse, in fact. If you multiply this matrix by itself, you get the identity matrix. Right? If we calculate P transpose AP, what we're going to get is what? I mean, I can do it since, I mean, 1 over root 2. There's 2 of them, right? P transpose 1, 1, 1 minus 1. What was my A? 1, 2, 2, 1. And then, so I'll multiply it out. I get 3. Well, surprise, surprise. So there you go. The symmetric matrix is diagonalized by this orthogonal matrix. As I said, a symmetric matrix is orthonormally diagonalizable. But there's more to this than just this. I mean, that's the main thing, that we can do this. But the other neat thing is, in this case, yep, go for it.
In our last mission, we had like similar questions to this at the end.
Mm-hmm.
Or I mean, on the eigenvector and eigenvalue questions.
Yeah.
Were you supposed to do P inverse AP to find the diagonalizable matrix, or were you supposed to?
It depends on.
P inverse and then make
depends on the question. So to calculate the nth power, so there's two different questions which were asked, which are different questions. The one question that's asked is starting with A, diagonalize it, right? So if I have A, then I can go to P inverse AP equals to D. This will be the diagonal. If A is diagonalizable, we can form P by concatenating the eigenvectors, the eigenbasis for A, and that similarity transformation will similarity transform A into the diagonal with the eigenvalues down the diagonal. A different question is to find A to the n. So to calculate A to the n, we do this. We say, well, A is equal to P D P inverse. And then because of the, when you multiply, the internal P's and P inverses cancel out. Right, so there we find a different pattern. But they're for different questions, whether, you know, that's why we had the P on one side versus the other. They're different questions. I know what you're talking about. So, comment. Okay. What's that? Talk about what? I'm sorry, I didn't hear. Limits of matrices. Not yet. Maybe. They are horrified by your suggestion that we look at limits of matrices.
Well, I'm horrified trying to write about it. So.
Ah. He's like, well, I have to write about it, so why can't we talk about it a little bit? Fair enough. But there will come the day that we should talk about that. We're not quite there. So how to build projectors via the eigenvectors. So here's the deal. That A we were just looking at, I'm sticking with that same example. I can reconstruct A as follows. It's going to be 3 times V1, V1, minus 1 times V2, V2. And that's not quite right yet. See, it has to be a 2 by 2 matrix. So you tell me, where do I have to put the transpose? If I want those to be 2 by 2 matrices, where does the transpose have to go? And if you didn't realize, I'm calling this V1, I'm calling this V2. Do I need to put a transpose on the first one? I want this to be a 2 by 2 matrix. I'm still continuing the same example. The second one. Otherwise we'd be looking at the dot product, right? If I put the transpose on the first one, we just got 2. Because these are orthonormal, so like v1.v1 is 1, v2.v2 is 1. So let's work that. What is that? That's 3. What's v1, v1 transpose? That's well, it's actually 3 halves. And what was v1? 1, 1, right? 1, 1. Minus 1 half. 1 minus 1. 1 minus 1, yeah. And I know you don't multiply those like that much, but this is 3 halves, 1, 1, 1, 1, minus 1 half, 1 minus 1, 1, minus 1, 1. In other words, you've got the matrix 3 halves, 3 halves, 3 halves, 3 halves, plus the matrix minus 1 half, 1 half, 1 half, minus 1 half. My claim is that if I call this the standard matrix of S1, and if I call this the standard matrix of S2, my claim is that those transformations, S1 and S2, are orthogonal projections. What happens with S1 if we multiply it by, V1? rather than actually using the matrix, I'm going to go back to its formula, which was 3 V1 V1 transpose V1. V1 transpose V1 is just 1, so this is just 3 V1. And how about what happens when we take the standard matrix of S1 times V2? This is V1 dot V2. That's 0. We've constructed, I mean, they're perpendicular, right? So that's 0. So what I'm trying to say here is the range of S1 is equal to the one eigenspace. The kernel of S1 is in fact equal to the 2 eigenspace, which, by the way, is the 1 eigenspace is perp. I mean, it makes this an orthogonal projector. Here's a kind of backwards question. Build a symmetric matrix with lambda 1 equal to 11 and lambda 2 equal to 300. So here's how I do it. I go, okay, I'm going to set B equal to lambda 1 times, well, V1, V1 transpose, plus lambda 2 times V2, V2 transpose. It's funny because it's too easy. Let's see here. Well, if we take B times V1, what happens? See, the thing is, whenever the V1 hits V2 transpose, that's 0 because they're perpendicular. I'm still using the same V1 and V2, okay? Still the same V1 and V2. So this is just lambda 1, V1. It's just that. Because V1 transpose V1 is equal to 1, and V2 transpose V1 is equal to 0. And likewise, BV2 is equal to lambda 2 V2. I mean, if you look at this, my choices of 11 and 300 are kind of immaterial, right? I mean, they could have been anything. This is my point, is once you have an orthonormal basis for R2, you can use those to construct a symmetric matrix with whatever eigenvalues you like. Yeah. I mean, I guess we could actually find out what that matrix is. It would be 11 over 2 times, what was it, 1, 1, 1, 1? Let's see here, plus 300 over 2 times minus 1, oh no, 1 minus 1, minus 1, 1. What is that? You're like, you should have picked 12 instead of 11, right? Yeah, what's that?
I said we're in 321, numbers are gross.
Oh, okay, numbers are gross. So that's apparently 311 over 2. Oh, hey, this is, oh, Now that's a sore subject right there. Let's see here. 311 over 2. Let's see. 2 minus 289 minus 289 over 2. Oh, you did? Check work. The determinant of B is supposed to equal to the product of the eigenvalues. The trace of B is the sum of the eigenvalues. Is that, what's the determinant here? So we've got 311 over 2 squared minus 289 over 2 squared. What's that equal to? Apparently, 311 squared minus 289 squared divided by 4. What's that? You had better tell me 3,300. But you have actually worked it out? Nah. I'm trying to safeguard against a, arithmetic mistake, right? It is 3,300? Okay. And what's the trace? The trace is what? Three 311, which of course is 300 plus 11. Now, how did I know that? I mean, I haven't told you this before, have I? That the determinant's the product of the eigenvalues, and that the trace is the sum of the eigenvalues. How do I know that? Let me tell you how I know that. The trace is the sum of the diagonals. So, if we're working over the complex numbers, all right? If you take a matrix A, right, you can take it and you can similarity transform it, P inverse AP, into the Jordan form of A, right? And the Jordan form of A, what's it look like? It's some sort of like direct sum, right? Over, Jordan blocks, right? Of particular eigenvalues, right? It's a direct sum of Jordan blocks. What's the determinant of P inverse AP? Well, it's the determinant of A, isn't it? Because we can, by properties of the determinant, move the P inverse around, and P inverse times P goes. So the determinant of A is equal to the determinant of P inverse AP, but the determinant of P inverse AP is also equal to the determinant of the Jordan form of A. But what is that? It is a product of the eigenvalues down the Jordan form. It's not diagonal, right? But it's block diagonal, and on the diagonal are the eigenvalues. So the determinant of the Jordan form is just the product of the diagonal entries, which is the product of the eigenvalues, right? I'm not using distinct labeling here. If I had like a 3 repeated, I'd write lambda 1, lambda 2, lambda 3, all for 3 in this notation, So it's lambda 1, lambda 2, lambda n, could be duplicate. And by the same reasoning, the trace of A is the trace of, P inverse AP, which is the trace of, J, however big the first, well, anyway, it's lambda 1, lambda 2, lambda n. And then there's stuff, in the upper diagonal, whatever, Not sure exactly, depends on the details, but the point is the trace is the sum of the diagonals. The trace is always the sum of the eigenvalues. So this is helpful as you're studying certain matrices, because the trace has to be the sum of the eigenvalues. This is still true for the real Jordan form, if you sort through it. But then you got conjugate pair stuff to think about. Okay. Now, next time, I'm going to show you, well, I'm going to show you something. Actually, I should get the projector out and show you something here. Oh, I thought we had till 1. Oh, hit the camera. I'm sorry, guys. Because I have muffins. Please take one of these lovely course evaluation forms. And when you're